Welcome to Tomorrow Unveiled.
It's great to be here. And, the past week, it was really pivotal, not necessarily for one single blockbuster discovery, but more for the foundational tech advancements, things that are collectively building, well, laying the bedrock for a really resilient and hopefully economically viable off-world future. The sources our research team compiled really show this concentrated effort, focusing on propulsion, manufacturing, operations, the core systems.
Exactly. And our mission here on Tomorrow Unveiled is to take all that detailed material and we'll show you how these pieces are starting to fit together, how they're fundamentally intertwined. So today we're going to unpack this really sophisticated dual track strategy the industry seems to be pursuing to conquer deep space distance. We'll also look at how manufacturing itself is actually moving into orbit. And there's this really critical lesson in resilience we just learned from a major cargo missions, a close call, a bit of a hiccup there.
Yeah, that was interesting. And these aren't just like minor technical tweaks. These are the absolute essential ingredients if we're serious about sustained human presence out there. So maybe let's start with the classic constraint, the biggest hurdle, just distance and time.
Okay, yeah, let's unpack the solution. The research team highlights this focus on high-performance nuclear power. But it's not just one approach, right? It's this dual-track thing you mentioned.
Right. That dual track strategy is absolutely crucial because different missions have different needs, basically. So the first track is nuclear thermal propulsion, NTP. Think of it as the sprint system. It's designed for, getting away from planets quickly, escaping gravity wells, and making fast transits between worlds.
And the potential payoff there, what stood out to me from the research, is just immense. We're talking about potentially cutting a crewed Mars round trip, from 3 grueling years down to maybe just 1 year? That completely changes the game for long-duration exploration, doesn't it? The human factors alone.
It absolutely does. And that huge leap in capability, it's enabled by some really cutting-edge concepts, like the centrifugal nuclear thermal rocket, the CNTR, that U.S. researchers are developing. It moves beyond the old solid fuel idea. Instead, it uses liquid uranium.
Liquid uranium, wow.
Yeah, liquid uranium in these rotating cylinders, and that heats the propellant directly. This concept promises to roughly double the engine efficiency compared to chemical rockets.
Double. So we're talking specific impulse, the efficiency metric, way beyond 900 seconds compared to maybe 450 for the best chemical rockets.
Exactly. And that efficiency directly translates into cutting the crew's exposure. Less time spent soaking up deep space radiation, less time dealing with microgravity effects, potentially cutting that exposure by 2/3. It's huge for crew health.
Okay, so that's the sprint. What's the other track?
So at the same time, you have the U.S. Space Force, really focused on the other half of the strategy. Nuclear electric propulsion, or NEP, that's the marathon runner. The SPAR Institute, for instance, is sponsoring research into NEP. Here you use a reactor, but just to generate electricity. And that electricity then powers these super efficient electric thrusters, ion engines, Hall thrusters, that kind of thing.
Right, so NEP is very low thrust. It can't really do that fast sprint you talked about. But the research suggests it can run continuously for months, years even, enabling spacecraft to, what was the phrase, maneuver without regret.
That's the idea, maneuver without regret. It means you can do long-duration orbital adjustments, reposition assets, maintain complex satellite formations almost indefinitely without worrying constantly about running out of fuel. The advantage is pretty profound. NEP could provide the same total change in velocity, the same maneuvering capability as a chemical system, but using maybe 10 to 50 times less propellant mass. That's a massive saving.
Okay, so they're not competing technologies then, they're complementary.
Completely complementary. NTP gets you there fast, gets you out of the gravity well. NEP gives you that agility and persistence once you're actually in space.
That makes perfect sense. Okay, so once we figure out how to get there quickly and then maneuver efficiently using nuclear, the next big challenge is building stuff, right? Setting up habitats, infrastructure. Is that where this idea of an industrial revolution in space comes in?
Precisely. And it actually starts with boosting production speed right here on Earth. Boeing, for example, our research team, highlighted how they're using additive manufacturing, 3D printing, to completely overhaul how they make solar array substrates for spacecraft.
How does that work? They're printing the whole structure.
Essentially, yeah. They're 3D printing the entire structural component. And the cool part is that lets them integrate things like wiring paths and structural supports directly into a single printed piece.
Ah, so consolidating parts, fewer steps.
Exactly. And that technological consolidation, it can compress the build time for a big solar array wing by up to 6 months. That's like a 50% production improvement for these big platforms, even up to large geostationary spacecraft size. Huge speed increase.
Wow, 6 months. That's significant for deploying large constellations quickly.
It really is. And then we see similar innovation actually in space. In space manufacturing, ISAM. Look at the UK's SpaceForge. They recently established contact with their ForgeStar 1 mission. It's basically a pathfinder for a returnable orbital factory.
An orbital factory? What are they planning to make up there?
Well, their high-value goal right now is producing advanced semiconductor crystals. Things like exotic alloys or perfect crystals that are really hard or impossible to make perfectly down here in gravity. See, microgravity, you can reduce defects in the crystal lattice, tiny imperfections, by maybe a factor of 100.
100 times fewer defects. What does that mean for performance?
It could potentially lead to something like a 10-fold increase in the final device quality or efficiency. So suddenly, a tiny chip made in space becomes exponentially more valuable than one made on Earth.
Okay, that's a serious economic driver, potentially.
Infinitely. But all this new activity building faster, launching more satellites, doing experiments in space, it generates just a staggering amount of data.
Right. And data needs infrastructure, even in orbit.
Which brings us to the Axiom Orbital Data Center node, or AX-ODC.
Okay, what's that?
This is said to be the first petabyte-class commercially operated data storage and edge computing platform. And it's going right onto the ISS, the International Space Station.
So edge computing in space, like bringing the cloud to LEO.
Pretty much, yeah. Its application is critical. It allows you to do AI, machine learning processing right there on orbit. That takes a huge strain off the data downlink capacity back to Earth, which is already getting crowded, and it reduces latency, the time delay.
Makes sense. Process the data where it's generated.
Exactly. And here's a really interesting detail the research team flagged. The communication terminal they chose for this commercial data center is explicitly SDA Tranche 1 compatible.
Wait, SDA, that's the Space Development Agency? That's military, right?
All right.
So a commercial data center is deliberately integrating with military communication standards. That sounds significant.
It's a huge signal, I think.
Yeah.
It suggests we're seeing a new shared technical standard emerge as maybe the dominant communication network backbone in low Earth orbit, blending commercial and military needs.
It points towards this technical integration of commercial capability and, well, national security resilience, doesn't it?
It certainly seems that way.
Okay, this is fascinating stuff. If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and maybe consider hitting that new hype button to help us reach more viewers. And of course, do turn on notifications so you never miss an update on the future. All right, let's pivot a bit now and look at how some of these new technologies and ideas are actually being put to the test right now, starting with basic logistics. Cargo delivery.
Yeah, Northrop Grumman's new Cygnus XL cargo spacecraft just successfully completed its maiden flight to the ISS. Big milestone for them.
And the XL version, that's bigger, right? More capacity.
Substantially bigger. It offers a 33% increase in cargo capacity over the older versions. Hauled over 11,000 pounds on this first mission.
That's a lot of supplies. But you mentioned a hiccup earlier.
Right, and this is where the most valuable lesson might have come from.
Yeah.
During the flight, there was a propulsion anomaly. It actually forced mission control to postpone the planned arrival at the station.
An anomaly? What happened? Engine failure.
Well, the main engine did shut down prematurely. Happened during 2 separate burns, actually.
Whoa. So what went wrong? Was it hardware?
That's the fascinating part.
Yeah.
It wasn't hardware failure. The root cause was traced to an overly conservative safeguard programmed into the flight software settings.
Wait, so the entire mission was almost jeopardized because of a setting, a software parameter.
Pretty much. Too cautious, apparently.
Huh. Does that make these newer software-defined spacecraft maybe more fragile in some ways, even if they are more flexible?
Well, it definitely highlights both the vulnerability and the strength, I think. The strength was that mission control could rapidly diagnose the issue because it was software they could validate a fix and then upload an alternate burn plan directly to the spacecraft. And it worked. You can just imagine the collective sigh of relief in Houston when they realized, okay, it's just a setting we can change, not some catastrophic hardware flaw.
Right. That ability to rapidly modify the software remotely, that is operational resilience in modern spaceflight, isn't it?
It's the definition of it. And that exact same software-defined architecture, that flexibility, it's absolutely central to the military paradigm shift that's happening in parallel.
Ah, you mean the SDA's work?
Exactly. The Space Development Agency just successfully launched the first operational satellites for its Proliferated Warfighter Space Architecture, or PWSA. They deployed 21 satellites for what they call the Tranche 1 transport layer.
And this represents that big shift, right? Moving away from a few huge, expensive satellites.
To a vast proliferated mesh network in low Earth orbit. Hundreds, eventually maybe thousands, of smaller, cheaper, and therefore more resilient satellites. If you lose one, it's not catastrophic.
Okay, and how do they talk to each other and to the ground?
The network backbone uses optical intersatellite links, basically lasers communicating between the satellites. Very high bandwidth, very secure. And critically, these satellites carry Link 16 terminal.
Link 16. Okay, for listeners who don't follow military comms super closely, remind us what that is.
Link 16 is the military's standard secure tactical data link. It's used by pretty much everything: tanks, ships, fighters, command centers, to share situational awareness data.
So putting that capability directly into this global LEO network.
It dramatically shortens the time it takes to get critical tactical information from anywhere in the world to anywhere else in the world directly to the warfighter. It's a huge force multiplier.
Okay, so we have intentional operational tests like Cygnus and PWSA, but space throws curveballs too. We need to talk about this unexpected stress test, the Interstellar Comet 3I-ALS.
Comet 8AS. This thing is truly unique. It's only the third confirmed visitor we've ever detected coming from outside our solar system.
An interstellar object, and it's moving fast.
Exceptionally fast.
Yeah.
And because it's an active comet, it has this big cloud of gas and dust around it, the coma, which is obscuring the solid nucleus. That makes it incredibly difficult to study, to figure out its size, shape, composition, anything, really. It's become this intense, unplanned test of our deep space tracking and observation capabilities.
So how are we responding? Can we even study it effectively?
Well, the research team detailed this major coordinated observation campaign that's being planned. The best opportunity looks like October 2025, when the comet makes a relatively close flyby of Mars.
Ah, so we can use the probes we already have orbiting Mars.
Exactly. Leverage assets already in place. NASA's Mars Reconnaissance Orbiter, MRO, will use its powerful HiRISE camera. ESA, the European Space Agency, will use the ExoMars Trace Gas Orbiter with its CASSIS camera, and also their Mars Express orbiter with its HRSC instrument.
So a multi-agency, multi-instrument effort.
Yes, and that coordination is absolutely crucial when you're dealing with these transient, unexpected targets. It really pushes the technological limits: instrument sensitivity, pointing accuracy, trying to characterize something that, well, literally wasn't supposed to be here, using equipment designed for much more predictable targets like Mars itself.
It really underscores the need for flexible, adaptable observation systems. But, even with all these amazing technological breakthroughs, faster rockets, orbital factories, laser comms, better cameras, the research team reminds us that there are still significant non-technical challenges, hurdles on the ground.
Oh, absolutely. Regulation's a big one.
Like with the nuclear propulsion we talked about earlier?
Yeah, the nuclear hurdle is potentially enormous. We have these really exciting developments in both NTP and NEP. Fantastic potential. But right now, there's just no clear regulatory framework specifically for these high-power, short-duration space nuclear systems. They kind of fall into this weird gap between existing rules for ground-based power reactors and small research reactors. And that uncertainty creates huge programmatic risk for the companies trying to develop these systems. They don't know exactly what safety standards or licensing process they'll ultimately have to meet.
Right, that ambiguity can really stifle investment and development. And is there a similar issue with the 3D printing revolution?
There is, yeah. Widespread adoption of additive manufacturing in critical space hardware faces what the researchers call a qualification gap.
Qualification gap,
Meaning because the additive process, building things layer by layer, fundamentally changes the material properties compared to traditional methods like casting metal or machining it from a solid block.
The old ways of testing might not be good enough.
Exactly. Traditional non-destructive testing, NDT, methods like standard X-rays or ultrasonic tests, might not catch unique flaws that can occur deep inside a 3D printed part. Remember, these parts are built up, layer by tiny layer. You could have microscopic voids or areas where the layers didn't fuse perfectly, hidden deep inside.
Ah, okay. So regulators and the engineers themselves need new ways to kind of see inside these printed parts, new testing methods.
That's right. They need new NDT techniques, plus extensive testing to validate the properties of these additively manufactured materials before they can be fully certified or qualified for something critical like a crewed mission to Mars.
So in a way, the hardware development is actually outpacing the paperwork and the rulemaking needed to approve it.
That's a pretty good way to put it. The technology is racing ahead, and the regulatory and qualification frameworks are struggling to keep up.
Okay, lots to think about there. Now, if you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It really does help us reach new listeners, and we genuinely love hearing your thoughts. So whether you're on YouTube or your favorite podcast app, please leave a comment and let us know what you think about this rapid acceleration we're seeing in space technology. All right, so let's try to zoom out a bit as we wrap up. If you had to pick one big takeaway from all the research the team compiled this week, what would it be?
For me, it's got to be the technological convergence. That's the headline. It's not just one thing happening in isolation. It's the ability to build faster on the ground.
Like the Boeing 3D printing,
Right. And then propel more efficiently in space.
the nuclear NTP and NEP.
Exactly. And then support operations more robustly with things like orbital data centers and these resilient satellite networks.
The Axiom node and PWSA.
Correct. All these advancements are feeding into each other, creating this really powerful, self-reinforcing positive feedback loop. And that loop is what's genuinely accelerating us towards, I think, a sustained human presence beyond just low Earth orbit.
That makes a lot of sense. It's the synergy between them all. Okay, so looking at the wider implications then, maybe a final provocative thought for our listeners. You highlighted that detail about Axiom's commercial data center deliberately using military SDA communication standards. As this commercial space economy really starts to take shape, how blurry do you think that line is going to become? The line between civil, commercial, and national security space?
That's the multi-trillion-dollar question, isn't it? When your critical commercial infrastructure relies on and integrates with military communication backbones, what new security challenges does that create? What new operational vulnerabilities? How do you manage traffic, prioritize data, ensure security in an ecosystem where the lines are just increasingly, well, blurred, especially beyond Earth orbit? That integrated future presents some profound questions we're only just starting to grapple with.
And that increasingly interconnected and potentially complicated future is exactly what Tomorrow Unveiled will continue to track.
Absolutely.
Thank you for joining us for this look at the future unfolding right now. We promise another deep dive next time on Tomorrow Unveiled.